speaker of this session is Aram Karakhanyan from Edinburgh. We'll talk about the question between fixed and free boundaries.
Proximity of free boundary to wedges and points. Thank you. Right. So first of all, I would like to thank the organizers for the invitation and for this opportunity. So the results I'm going to talk about are taken from a joint paper with Henrik Shagolan. And let me state the problem. So we're considering the two-phase ultra-fairly frequent minimization problem in a half ball. And we are prescribed some boundary data, say F. And the most important thing about this F is that on the flat portion of this unit upper ball, this F behaves like a wedge. In other words, the restriction of this F on a pi is going to be something like, say, alpha plus x2 plus minus alpha minus x2 minus plus some gx, where our gx is of order small x. So just let me draw a cartoon picture just to explain what's going on. So say this is xn plus 1, and this is, say, x prime, which is our pi, and this is x1. So we are prescribed something like this. So this is the boundary data. So it's like a piecewise linear function. This is the origin. And this is, say, b1 plus. And then we're trying to find local minimizers of this problem subject to this boundary condition. And we're interested what happens to the free boundary near this origin. In other words, if I just draw another picture now, like n-dimensional picture. So this is x1, and this is called x2, which is again, well, this is r minus 1 in some sense. So you want to see what's the behavior of your free boundary near this origin, right? So there are a few assumptions regarding these constants involved. Well, the standard one, that's the main one actually in our Friedman paper, is that, so let's just denote this by big lambda. So I'm assuming that this constants, lambda plus and lambda minus, satisfy this condition. And I'm also assuming, so in this picture, basically, you can assume that your G is identically 0. In that case, you're going to get the standard, like, piecewise linear function where the C1 kind of continuity breaks down at the origin. All right? And just let me say that we will see that, I mean, the main result, which I will be able, hopefully, to formulate before the end of these 30 minutes, says that you're going to have something like a wedge, and these two planes will be determined by the largest and smallest global homogeneous solutions, homogeneous profiles corresponding to these problems, and you're going to have tangential approach of your free boundary to either of these planes. In one phase case for any dimension, and in two phase case for dimension n equals 2. All right, so this is the game that we are trying to play. So let me start now from discussing the main kind of steps towards proving this theorem. So the first result is about the optimal growth of our minimizer away from the free boundary. And the optimal growth is going to be basically linear thanks to the scale invariance of this function. And I'm going to separate between the one phase and two phase cases. So suppose that n is bigger than or equal than 2, and the origin is non-isolated free boundary point. then we have that u, well, in this case, u is one phase, it's non-negative, so it's going to be, there exists a constant c, positive constant, such that this is satisfied for some positive constant c, say in 1/2 plus, say in a half pole. And as for the two-phase case, I'm going to make an extra assumption about the free boundary, and I'm going to call that delta thickness, which says that if you're considering the
Careful with the cable.
sorry.
Careful with that cable. That's for the don't push that cable.
All right. It's good to know. Some accident will happen. All right. So delta thickness says that if you are considering two concentric balls, say P, say Q rho plus, and this is P rho plus, and you're considering your free boundary, then there exists a positive delta such that, so if you take a delta cone here, then this intersection is always non-empty. So the free boundary, and this is intersected with 1/2 plus. So this is non-empty, meaning that you have sufficiently many free boundary points lying above this cone and inside of this like half-annular domain. So if this delta thickness condition is satisfied, then the same. Hopefully I didn't touch the cable. So then we have the linear growth. In other words, you will have that now mod x, mod u of x, because now you have two-phase case. So this linear growth estimate holds, say again in u1/2 plus. Okay?
I'm sorry,
Yeah.
what is the delta in the...
So delta is this basically the angle of the cone.
But where's in the formula?
In the formula, I don't see it.
Where's the condition?
Oh yeah, right. Right. So let's call that K delta. Yeah, so it was on the picture, but was sorry about that. Yeah. So for some positive delta, it's not really important what the delta is. So the idea is that you want to stay kind of uniformly above this flat portion of your fixed boundary by size delta, and this is crucial in two-phase setting. And now, just want to say a few words about the proof. The proof is based on dyadic scaling argument, and it works perfectly fine if you consider the one-phase problem, but then for two-phase problem you run into trouble if you don't assume that delta thickness condition. Okay, the sketch of the proof. So what's this dyadic scaling argument? So this is basically a very useful technique that you can apply to fairly large class of free boundary problems, one-phase problems. And it says that, so if you consider this quantity, say Sju, so this is the supremum of mod u in B1, say, plus 1 over 2 Qj, okay? And then, say, you take rho j to be 1 over 2 to the power j. Then dyadic scaling says that instead of proving this linear growth, it's enough to establish the following estimate, that this Sj plus 1u is less than or equal than the maximum, some positive constant c, to the power minus j over 2, and then S of j of u over 2 s j minus 1 u 2 to the power q, etc. And then s0 u over 2 to the power j plus 1. Okay? So if you have this inequality satisfied, then that gives you linear groups. So for some positive constant c, because it's kind of the argument that you use in the George's in the proof of the George's theorem, you take your favorite r and take two corresponding powers such that this r is entrapped in this dyadic in one of these dyadic intervals. Then using this and iterating, you can show that this implies that your the supremum of u over, say, dr is less than or equal to 2 times c times r. Okay, so this is the effect of this dyadic scaling argument. And in order to prove this, we argue towards contradiction. And if you do that, you basically negate this statement, and you get that there exists a sequence of kj's such that, and actually also a sequence of local minimizers of our problem such that you have the following inequality. So instead of, so basically in this inequality, it's crucial to assume that you have some c for which this is true. If that's not the case, you can take your c arbitrarily large. In particular, you can take c to be j. So it will become j times 2 to the power minus kj over 2, etc. And then going to get skj minus n uj to the power n plus 1, etc. Then s0 uj to the power kj plus 1. And then you consider a scaled function, say vj, which is defined as uj rho kj plus 1x. Sorry, just the kjx over s kj plus 1 uj. And then you check that, in fact, this function, this sequence of functions, enjoys a number of interesting properties. And then you can use a customary compactness argument and conclude that they converge to some v0 in some Hilbert space, say v plus r for any finite r. And then you will have that this limit function is non-degenerate. In other words, the supremum of the modulus, the supremum of the absolute value in, say, half ball is going to be 1, due to the fact that here I have this j. So basically that gives me that if I just move this here, I will get that. So basically it gives me that rho, if I just rewrite taking this bit and this bit, and I rewrite, I get that rho kj over s kj plus 1 uj is less than 1 over j. In other words, this quantity goes to 0 as j goes to infinity, right? Due to this fact, if you now use the scaling property of our functional, the resultant scaled function is going to minimize something like the standard Euclid energy plus 1 over this quantity. In other words, rho rho kj over s kj plus 1 uj square, and then that lambda function, which is bounded because here you have the characteristic functions, okay? And this kills off this characteristic function, the bounded term, and in the limit, you're going to get a harmonic function. So our limit function to 0 is going to be harmonic in Rn plus, in a half space, okay? And finally, fourth one says that V0 is going to have a linear graph. Okay, now that done, the only extra piece of information is missing from this list to conclude the contradiction is the existence of a point where my function vanishes, right? Because basically from these conditions you can conclude that your V0 is going to be a linear function, x1 plus or something. Well, just x1, right? And for two-phase case, if you assume that the delta thickness condition, which I won't erase, so if I have this condition satisfied, then in addition to these four conditions, I'm also going to have a point, which is, now this is the delta, so I have some y0 where my limit function vanishes, right? Which will be a contradiction because this function will never vanish, right, if you are here. Okay? So this is for two-phase case plus the delta thickness.
We're going to on the boundary condition.
Well, boundary condition is linear, and again, due to this fact, it just kills off everything. So here you're going to have that your V0 is going to be identically 0 on this flat portion. Okay. And now, how about the one-phase case? Again, it's enough to conclude that somehow you manage to get a point, which is again uniformly above, in the sense of this cone, above this pi, where your function, the limit function, vanishes. And to do that, you use very geometric argument, kind of a rolling ball argument. Say this is the two balls. So remember that these are the powers of, so rho kj is 1 over 2 to the power kj, right? And so we are now in one-phase case. And here, say you have the free boundary. So we assumed, actually I erased that, but I emphasized that it's important to assume that your origin is a non-isolated free boundary point. So if you have that, then you can take a ball. Basically, the ball is going to have the half of the distance between these two spheres, and then you just roll it, keeping it inside of this angular domain, right? So at some point, this guy is going to touch a free boundary point, right? And at that free boundary point, Al-Kafreli says, since we are in one-phase case, it says that here your gradient, say this is xj, right? So this is going to be bounded by lambda plus, okay? A lambda plus is a universal constant. It was appearing in the formulation, in definition of the functional, and therefore now you use the very standard kind of Hopf type lemma and conclude that at the center of this ball, you're going to have that your ux is going to be less than or equal than some universal constant times the distance here, say pj times this lambda plus. And this pj is 1/2 rho kj minus rho kj plus 1. And this is 1 over 2 to the power kj plus 2. All right? And therefore, now if you rescale, and again, use the fact that this ratio goes to 0, and so basically this goes to here, and then you also divide everything by this skj plus uj, you will get in the limit that here you're going to have a point which is going to be uniformly above this plane, due to the fact that if you just try to see what's going to be the angle here, then say alpha, right? Then the tangent of alpha is going to be bigger than equal than this pj over, so it's going to be something like rho kj plus 1. And this is going to be like 2/3. Right? So this is kind of your delta in this situation. Right? And then you conclude the linear growth. Now next result is to classify the homogeneous, global homogeneous blow-up limits. And that one is easy to do if you work in two-dimensional setting, because then you have explicit computation. I'll say theorem B is about global solutions. For global solutions, so again I'm going to consider two cases. So one phase case plus so in this case your n is arbitrary, and then in two-phase case, I'm going to assume that n is 2. And then if U is homogeneous global solution, then I have these only two global solutions, which are going to be piecewise linear functions. So that's alpha plus and alpha minus that just come from the boundary condition. Okay, and so this is actually going to be the smallest solution, smallest global homogeneous solution, not actually homogeneous, just the smallest global solution is going to be this. In fact, smallness forces this function to be homogeneous. And this is going to be the largest global solution. In other words, all other global solutions that you're going to get, in particular, any blow-up is going to be a global solution. That guy is going to be trapped between these two. Okay? And as you can see, so the free boundary, so what's the free boundary of this one? So the free boundary of this one is this plane. Well, minus x2, right? And then from here you have plus, so you get that these are the free boundaries corresponding to these two homogeneous global solutions. In fact, if you consider one phase case, then this bit just disappears because then your alpha minus should be 0. Okay? Now, what's the main technical difficulty proving this? The main technical difficulty in high dimensions, so if you consider, say, n is bigger than 2 and you consider two-phase problem, main difficulty is that in one-phase case, you know that the free boundary is a generalized surface of non-positive mean curvature. This means that if we're considering, say, the free boundary, say, here u is identically 0, here u is positive, so this is the free boundary, and then you take some so I should say U0, so this is a global solution. Then if you take your favorite piece, say S of your free boundary, and then you perturb it, so call it S prime, such that the perturbation is entirely lying in the positivity set. Then the perturbed surface is going to have bigger Hn minus one dimensional measure than the original one. So then you're going to get that the size of S is less than or equal than the surface for Hausdorff n minus one dimensional Hausdorff measure for the perturbed one. And this is due to the fact that for global solutions, the gradient is always going to be bounded by lambda plus. Okay, so just to see this, you just integrate your Laplacian inside of this domain, just cleverly separate the integrals and you get that. So this is not true. I mean, this is not available for two-phase problem. If you are in dimensions higher than 2, then this doesn't work. And there's a crucial, actually, fact that one uses in order to get the this formula for global solutions. Okay. Just want to check how much time do I have.
2 minutes.
2 minutes. Okay, and now I'm ready to formulate the main result. It says that under the conditions above, I have the following limiting wedge configuration. So let's call this theorem C. Now, so think that these are the free boundaries. So this is, think that this is x2 and this is x1. So this is the free boundary of the small one, and this is the free boundary of the large one. Then main theorem says that under the conditions above, say one phase and n is bigger than 2, and then two phase and n is 2. For any r that you give me, r is small, I can find two wedges containing these free boundaries and say that the size of this wedge here is given by sigma r. So this is the modulus of continuity of the approach of your free boundary to this wedge. I have that.
I think your pictures are deceiving. I'm sorry.
Sorry?
Because it goes like this.
What do you mean it goes like that? Well, this is kind of a neighborhood, like a wedge neighborhood of the free boundary.
But the sigma r, there it goes like this, like a cusp. Oh, this means that you have a distance, but actually the picture is like this. If I'm not wrong.
Okay, so let me say this. So basically, that measures the size of the aperture of this angle. So how small is this?
So
Does that make sense?
That goes to 0 with the.
That goes to 0. R goes to. So in other words, it's
Yeah, but in comparison with the distance, so it goes faster.
But I didn't say anything about sigma, right?
So that's why I'm saying that the picture is.
No, but I didn't say
Okay,
what's
go
the
ahead.
sigma. So
Sorry.
the idea is that if you take your r sufficiently small, I can make this sigma as small as I wish. Well, as sufficiently small. In other words, I can reduce the aperture
Yes,
here
exactly.
smaller and smaller as your r tends to 0, and then you will get that for any u, the free boundary of this is going to have tangential touch with either of these two free boundaries to these planes in this sense, in the sense of these wedges. All right? And for if you have tangential touch, so this is like remark. So if you have tangential touch to Vs, then that's the modulus of continuity is uniform. It doesn't depend on a particular solution that you take. Because actually, I didn't have time to say about that, but this is due to the fact that the smaller solution has larger Weiss energy than the larger global solution. Right, so I'll stop here. Sorry for running out of time. Thanks for your attention.
Any question?
Hi, couple.
All right.
Well, so first of all, I didn't really understand this cone condition, the delta. So you ask for given a delta, this thing with the balls of radius rho and 2 rho holds
Yes.
for any rho.
Any row, yes.
And is that
That's artificial condition, I have to admit that.
so? If there, I mean, basically, you don't want the free boundary to go.
Well, but
along
what
the
the,
axis.
the moral motivation is that you don't want your free boundary to get closer to the flat portion. In other words, you want to your free boundary to stay sufficiently above of the flat portion in terms of that condition.
Actually,
And
there's a
avoiding-
counterexample to that.
You have a
Of
counterexample,
course,
but don't
because it's just go for solutions to the harmonic functions with Lipschitz data. They're not C1.
Well, it's not quite the counterexample I guess he means,
Well,
but
C1, it's not C1.
no, no,
Lipschitz. They're not Lipschitz. So Lipschitz data doesn't mean Lipschitz solution is.
No.
no, I think he's asking just about the justification of the thickness condition.
Because if you construct the Remember we constructed the example which goes down
Yes.
tangentially, and that you cannot deal with.
But with those boundary conditions.
Yes.
Or one-phase case.
So just do Poisson representation and you will get that.
Well, you're always going to have these logarithmic wiggles. I mean, without further, but the condition is not optimal. It's like we cannot say that it's kind of the best condition.
No, but
That's kind of what helps us to get around the problem.
Maybe I can also remark one thing is that there are actually solutions that are inhomogeneous. They go like this, global solutions. That are inhomogeneous. So you have to sort of.
I mean, we had the classification for global homogeneous, but you might have global solutions which are not homogeneous. And so that's another technical difficulty that factors in.
so these are unstable somehow. Can you?
So
can they-
this is
if you-
unstable, this is stable. Because, as I said, so you have this comparison of Weiss energies.
Right.
And due to that fact, so this one turns out to be stable.
But if you perturb the boundary data, that one can.
That was
jump
that,
to
that was yeah, that was what Henrik was saying. So do that even by some very small epsilon perturbation, we can go from here to here, and that will give you, as a result, it will give you that you have a non-homogeneous global solution.
Okay, I think I'll stop with this, so thank you.